Okay, I want you to go ahead and write these problems down. We're going to divide Chapter 15 into 2 parts, and these are the problems that I want you to do for that. And I do want you to read the chapter. So make sure you write those down. All right, so as you're writing those down, I'll talk about the new things that we're going to be learning today. Previously in Chapter 14, we've been dealing with disjoint and independent events. And we've got a good handle on finding the probabilities for disjoint and independent, but what happens if they are not disjoint or independent? Gasp. So we're going to develop a general rule for the addition of probabilities and a general rule for the multiplication of probabilities. Okay, so here we go. You recall basic probability is this. Probability of the count of outcomes that you want out of all possible outcomes, but sometimes they overlap and they are not disjoint. So remember that when we wanted probability of A or probability of B, everything we've been doing so far has just been A or B because they've been disjoint and not overlapping. But in actuality, union A or B is really probability of A, probability of B, or it could be both if they overlap. Therefore, you have to watch out for those probabilities that actually have both. Drawing a picture will help you with that. The best picture is a Venn diagram because you can see how much is extra or maybe got counted twice when you did your addition. Okay. So when 2 events are disjoint, then we can just simply add. However, when you have this overlapping area, if I added A and I added B, what would have just happened? Good, I'm doubling the overlap. So, but if the events are not disjoint, using the rule above would end up doubling the section in the middle. That is overlapping. Therefore, we must use a general addition rule. Okay, and here it is. Our probability of A or B is going to be adding the A, probability of A, plus the probability of B, and subtracting away the overlap. Okay, so we're going to subtract away, and the overlap is the probability of A and B. All right, so let's go ahead and fill in some of our notes. Oh, and there they are, because I left that on, I guess, accidentally. So let's do this way so we can talk through it. So, if the events are disjoint, then we have probability of A or B as just adding them together. But if they are not disjoint, explain why this formula does not work. Why does that formula not work? Good. The amount in the middle would be double. It would double count the middle. All right, very good. Next, in general, whether events are disjoint or not, what is the formula finding for probability of A or B? A or B or both. Very good. Okay. Oh, what is the formula? Well, the formula is the probability of A plus the probability of B, and then subtract away that double counted portion. Okay, good, which we already discussed. Now, next question. Explain the difference between addition rules for disjoint and the general addition rule. So, the way I did this earlier was this. Okay, for disjoint, we know that the probability of A plus the probability of B is fine because there's no overlap. There's no overlap if they are disjoint. Okay? So what happens if, so here's the general addition formula, but what if they are disjoint? What does this portion right here actually equaling the probability of A and B. If they're overlapping, that portion is actually what? The overlap of disjoint events is 0. So do you see how if they're disjoint, then these would actually what? Be identical. Very good. So they would actually equal each other. Okay. So the difference is, again, this portion here, where if they are not disjoint, then that has a value. Okay, but in disjoint, they would be identical. Okay, so we're going to go on to some questions. And I had saved this, unfortunately, with all my writing in there. There you go. And I didn't want that. But we'll save ourselves some time, I guess. All right, the probability of, okay, so here we have this problem. When a random student from Aledo High School is chosen, and you have these in the back of your section, actually. It says some problems to do with Chapter 15. There you go. If you turn your notes page over. When a random student from Aledo High School is chosen, the probability that the student is a girl is 0.525. The probability that the student plays a sport is 0.443. The probability that the student is a girl who plays a sport is 0.221. Okay, so what would event A be? Well, that would, I guess, be the girls, but, I mean, the random, see, and again, I'm using event as a trial type thing. So randomly, I shouldn't have said event, but randomly picking a what? We got randomly picking a what? A girl, and then what would the other event happenings be? Good. Randomly picking someone in sports. Okay. So I think it would be helpful to see where the overlap is. And I do not want all that there. Let me go ahead and okay. Yeah, we won't worry about that. Okay. All right, so here is our sample space of all Aledo High School. And this is going to be our girls. And this is going to be our sports players. Okay? And so what goes where? How many played both? 0.221, okay. So how do I get this area over here just girls? Yeah, 0.525 does not go here because that includes the 0.221. Now you have too many girls if you do that. You don't subtract half, no? Yes. Take away the part that's accounted in the double counted part, and that will be 0.304. So 0.304 is the portion of Aledo High School that's just a girl that doesn't play sports. Okay? All right, how about this sports situation here? Well, 0.443 people play sports, but that's not what's only sports. That includes the girls, so how do I find out only the sports players? Subtract away the double counted part. And so this is the portion that is only a sports player. Okay, what else is there? That includes some boys in there, yes. That would be the boys that play sport. Very good, yes. Because right here would be my girls that play sports. And then over here would be my boys that play sports, okay? What's out here? Boys that don't play sports. Are girls out there? No, because this is the rest of the girls over here. Okay, very good. So how much is that out there? 1 minus all the rest. Okay, and that's 0.253, I believe. Okay, so let's answer our question. Find the probability that the student is a boy. Yeah, how about if we just say not a girl? Okay? So y'all don't get too caught up in all the little things we just segmented off. Just think not a girl. So there you go. So 0.475. All right. How about the probability that the randomly chosen student was neither a girl nor played sports? And you know how I'm all on you about showing work, and that would be incomplete. So instead of like, I mean, where is your work? Isn't your work up in your Venn diagram? So where is the part that's neither a girl nor played sports? That would be, okay, so that represents my Venn diagram. Is this what I'm wanting? Okay, so see, that's work right there. And then I already know from up above that that's 0.253, okay? So that work is supported by your Venn diagram that you've already drawn, so I'm good with that. Yes, what? No. I mean, you need to draw this. This is a real simple sketch to represent that this is where you got your answer in the Venn diagram up above. Okay? What's the probability that the randomly selected student was a girl that did not play sports? So where are my girls that do not play sports? Okay? All right, so in the circle portion, that's this right here, isn't it? Okay? So that's how I show my work there, and that was 0.304. So what's the probability that a randomly selected student was a girl or played sports? What else does that mean? Or played both. I mean, they could also play both. Okay. So a girl or played sports, but make sure you're only counting the middle once. Okay. So we can do this a couple different ways. If you're just incredibly visual and you want to do that from your Venn diagram, that would be 0.304 plus 0.221 plus 0.222, which gives us our 0.747. Okay. Now, formula-wise, what that exactly is asking is what our definition was, is saying the probability of a girl or sports. And from our formula, we know that that's going to be probability of a girl plus the probability of the sports, and then what? Subtract the girls and sports because they got double counted. So you would say 0.525 plus 0.443 minus the double counted part, and guess what that equals? The same thing as up above. Okay, so there's different ways for you, the visual people or the formula people. Okay, all right, now let's do conditional probability. Back in Chapter 3, we had looked at contingency tables to determine conditional distributions, and we also had looked at independence from that. Okay? So here's a picture of people's favorite TV shows based on and their school that they attended. All right. So let's say when we want to determine the probability of one event given the condition of another, we're going to write this. Probability of A given, probability of B given A. Or you can switch those numbers around, doesn't matter. Okay? So this little line right here means given that, so probability of A given that A occurs. Okay, so what I want to do is I want to take this chart and I want to walk through building that formula, because I think going that way, at least for me anyway, that makes it make much more sense. So here we go. Okay, let's first fill in these totals here, which I can give you. 95 in high school, 100 in middle school, 108 in elementary, 303 total. Of those students, 165 preferred SpongeBob, 55 preferred iCarly, and 83 preferred One Tree Hill. So, find the probability of randomly picking a student that is in high school and has SpongeBob as his or her favorite TV show. So that's this, SpongeBob and high school. So what is that? Where is that? 25. So that would be my 25 out of my total students of 303. Okay? All right, next. Find the probability of randomly picking a student that is a high school student. Correct. That would be my total of high school, which is 95 out of my 303. Okay. Now from that, I want to build this. Now find the probability of a student liking SpongeBob as his best, given that he is a high school student. So given that he's a high school student, how many is it going to be out of? Okay, it's going to be out of 95. And how many of those liked SpongeBob the best? 25. So really, it's a combination of the two of these things together. It comes from probability of SpongeBob and high school on top, so that comes from right here, look down here at this formula, probability of SpongeBob and high school right here out of the probability of high school. It reverses it here. I wish they would have done B and then A. I like to do it that way. Probability of B given A. It's the probability of B and A, so this is SpongeBob and high school. You like SpongeBob and you like high school out of the probability of being in high school. Okay, so does that make sense? You see how that formula comes about and gets built. Now let's fill in our notes. Oh wait, we might do some more. Yeah, we do a couple more samples of it. Okay, let's do some more samples. All right, we're going to find the probability that you liked iCarly given that you were in high school. So that's the people that are what? In iCarly and in high school out of what? The ones that are in high school. Okay? So how many is that? How many like iCarly and are in high school? So that's the intersection of those. What's that? 20 out of 95. And you know, you would simplify this or write it as a decimal, whatever. I think I just happened to have mine as a fraction today. All right, here, how am I going to figure that one out? The probability, first of all, it's given that they're in elementary, so the probability of elementary is down here. Now, what's the probability of the top? What's that going to be? They want One Tree Hill and elementary. How many of them were there in that category? I think 3. 3. But then if you reduced it, it would be 1 out of 36. Okay? All right. Now, I reversed this last one. What's that? Yeah, out of the probability of SpongeBob. So what's on the bottom? Given that they like SpongeBob, 165 like SpongeBob. What's up here? My elementary students that like SpongeBob. And so how many is that? 80. Okay. Good. That reduces. I just use math fraction on my calculator. All right. I think now we go fill in some of our notes. Here we go. Let's fill in 4 through 7. Back to your notes. What do you think is meant by joint probability? Well, simultaneous occurrence at the same time, okay? And, yep. Okay, so in essence, what is that? A joint probability is the intersection that we all love and know very well. So I just wanted to expose you to another vocabulary word there of joint. Okay, but how about conditional? What would be meant by conditional? No, not conditional. It's conditional upon something else happening. So how could you phrase that? No, not not independent. And okay, how about this? It would be the probability of a certain event conditional upon, I hate to use the same word in the definition as conditional upon another event having occurred, having had occurred, or whatever. Just don't get the English people in here. Or they would not like the way I spelled that either, okay? Yes, this is like given, yes. Yes. This, so for example, well, and you can't really say it's dependent, but, well, yes. So like A given that B happens. The probability of A given that something else happened, okay? All right, so let's do that formula. Yes, probability of liking SpongeBob given that you are in high school. Okay, good. State the formula for finding conditional probability. Okay, let's say this. Probability of, and I'm going to write A's and B's, but you naturally understand it as SpongeBob in high school. So the probability that you like SpongeBob given that you are in high school would be the probability of what? Both of them occurring, that you're a high schooler who likes SpongeBob out of the probability that you are what? In high school. And so that would be that. Okay? Given this, this is always the one that it is out of. Given this, this is always the one that it is out of. All right. And number 7, is the probability of A given B the same as the probability of B given A? No, why not? Okay, good. Their fractions will be different. Because if I say this, the probability of A given B, the top number will be the same, but what's going to be different? Okay, what's this one going to be? Probability of B given A. This one is the probability that you're in high school given that you like SpongeBob. That would be the same thing on top, all the same people on top, but what's on the bottom, instead of it being out of high school, what's it out of? The SpongeBob people. So because these numbers are different, these fractions are not going to be the same. Okay. All right. Let's move on to our next topic. That was 7. That was number 7. Okay, so here's now our general multiplication rule. And let's see, I think I have something there for you for that. Our general multiplication rule comes from this. Well, when they are independent, it's just probability of A times the probability of B. But if you cannot tell that they're independent and you haven't done an independence check, which we're going to learn about, then you have this. For any two events, it's going to be this. Probability of A and B is the probability of A, and not times the probability of B, but it's the probability of B given that A happened. Okay, so this would be like you pull a white shirt out of you pull out a white, what's the probability you get a white shirt out of your drawer? And this would be, what's the probability that you get another white shirt given that the first one you pulled out was a white shirt? Okay, you know, that's like without replacing. You pull a white shirt, say you have 10 shirts in your drawer and 5 of them are white. What's the probability you get a white one? 5 out of 10, okay, 1/2. But this probability of getting another white one would be now 4 out of 9 because it's given that that one already happened. Okay, but let's go into that. Let's do some specifics. So here we go. Using a table, it's fairly easy to calculate. For instance, what's the probability of female and right-handed? So that would be our 44 out of 100. And I should have probably used a table here, but I didn't want to have those. Let's say now we have the same information from earlier where we're talking about Aledo High School and the girls in the sports. Given, right here's the question. Given that a selected student plays sports, what is the probability that the student is a girl? So I would have to go like this. The probability of what? The probability of me picking a girl out of just the what? Sports players. Good. Given that the person is a sports player. So see, it has now dwindled it down to just my sports section. Okay, so how would I write that? On top, what do I have? Girl and sports. Out of sports. Good. Because that's what it's out of, given that it's that. Yes, given that they play sports, so it's out of my sports players. So now I've taken all of Aledo High School, and all I'm looking at is my sports players, and I want to know what's the probability that I pick a girl out of there. Yes. So what was our girls and sports? 0.221. What's our sports at Aledo High School? 0.443. And so that would be our conditional probability is this. So of all the sports players, about half of them are girls, is what that's saying. All right. Okay, let's answer 8 and 9 in our notes. So you're kind of moving back and forth. What's our general formula for finding the intersection if we do not know they are independent? Probability of A and B is probability of what? A times the probability of B given that A occurred. Okay, and then this is my favorite thing, which I'm going to try and squeeze in right here before we get done. Explain the difference between the multiplication rule for independent events and the general multiplication rule. Okay, if they are independent, it's just this. Okay? So that's for independent. Okay? So let me write the general rule over here. Okay. Let's just say that I know that they are independent, and let's discuss this right here. If I know they are independent, this says the probability of B given A happens. Okay, so follow me here. Probability of B given that A happens. What if they're independent? By definition, if they are independent, then what?
A doesn't matter.
Then A doesn't matter. Great. Excellent. If they are independent, then A does not matter. Therefore, this, in actuality, is just the probability of B because A didn't matter if they are independent. So what would happen then between those two? If they are truly independent, those two things would equal each other. Okay, very good. All right. Now, if this is different, then of course they were not independent. Okay, where are we here? So that gives us our definition for independence. So you might need to write this down. The probability of B given A would be just the probability of B. And that is because A would not have affected it. This A happening does not affect the occurrence of B. So that is a test for independence. So in your problems that you come across that ask you to determine if something is independent, for example, this one right here, which I think we might run out of room, so I'm going to kind of give you some answers real quick. Here we go. We're about to run out of time. So I would want to see, let's say A is being female, and B is being right-handed, because that's what it's asking. So it's saying, tell me if it's independent of gender. That would mean, is the probability of being right-handed, given that you are a female, what? Probability that you are right-handed if you are a female. If gender doesn't matter, it should be the same probability as just being, in general, right-handed. Okay, so let me say that again. You got to think about that. Probability of being right-handed given that you are a female. If they are independent, then being a female doesn't matter. Your chance of being right-handed is the same regardless. So if it is independent, which that's what you're wondering, is it independent, then your probability of being right-handed is the same regardless of whether you are a female or not. So that is how I check for independence. Okay, so I would go through my math and say, okay, well this here is 44 out of 48. Wrong. 44 out of 87. Nope, 44 out of 48. How many are, this right here, this number, how many are right-handed and female? That's 44. How many are just female? 48. Okay. What's the probability of being right-handed, just flat out plain probability of being right-handed? 87 out of 100. So the question is, are those things the same? And this is 0.917, whereas this is, of course, 0.87. So what would you say? That being right-handed is not independent of gender. You are more likely to be right-handed if you are a female. Okay, well, we don't know about that, but I could go through the process of being a male and see that.
Well, when it's only like 4 left-handed female, like that's all the number is going to be off by it.
You think it's going to be off because, okay. All right, so there's only 0.04 difference?
All the probability of something happening, I think left-handed probably is so small that you need more people to actually probability.
Like the law of large numbers, the greater that the farther you get along. Okay, so here's number 10 of your notes. Write that down really quickly. Here is a test for independence. Okay? Probability of B happening given A would just be the probability of B, because if they are truly independent, then the fact that you are female or whatever should have no bearing. This says that regardless of A happening, the probability is still the same for probability B. In other words, given that A happened, it's not affected. Okay, so that's it. We did have one other example, which we'll go into next time on tree diagrams. I know that none of your homework incorporates a tree diagram, but the homework the next time after that does. So here's the homework one more time, if you did not get that written down. Oh, this was last time. Okay, sorry, next. There it is. Ta-da! That's chapter 15.